Good evening. So in week 8 content, they mainly discussed about activation function, then what is batch normalization, why normalization is required, and then recurrent neural network, the different types. Um, so these are the main content that are discussed in week 8. So starting with the activation function. So, activation function is mainly used to introduce nonlinearity into the neural network. Without it, any number of stack layers would simply be equal to a simple linear transformation. So, activation function, it will take the input that it receives, that is the sigma wi xi, and then maps it to or transform it to a specific output. Now, there are different ways of transforming it, and some examples of those functions are this sigmoid, tanh, ReLU, leaky ReLU, exponential linear unit, etc. So, in case of sigmoid, the output, so whatever input it receives, it will transform the input to an output in the range 0 to 1. And the equation for, so if x is the input, the equation for sigmoid is given by 1 by 1 plus e raised to minus x. And the curve is like this. It is centered at 0.5. So one important point here is the saturation. Saturation means the gradient with respect to argument goes to 0. That is, when the grade, so if you see the graph, when the values are very large positive and when the values are very negative, then the curve is flattened. So when for large positive value, the value is 1, and for large negative, the value is 0. So when the input to the sigmoid function is a very large positive value or very large negative value, then it will saturate at either 1 or 0. Then what happens is the gradients with respect to this argument will become 0. So that is the saturation thing. And it is not zero centered. Outputs are always positive. Update of the weight will happen in the same direction. So that means it will be the output, the output from the sigmoid is always positive. So the difference you will understand with respect to tanh. So tanh is given by this function which has an output in the range of minus 1 to 1. And here also, because this flattening exists for a large positive and large negative, there is saturation problem. And this is centered around 0, which is good because it will help with optimization. So here it's not 0 centered and the outputs are always positive. But here it is 0 centered and the output sometimes will be positive and output sometimes will be negative. So there is a balance. So to reach to an optimal minimum or an optimal maximum, there should be a balance of going in the positive direction as well as a balance in going into the negative direction. It should not be like always going the same direction. So that's why this is a very, this is a good thing for optimization. Now, some of the other activation functions are this ReLU, leaky ReLU, and ELU. So ReLU is given by maximum of 0, x. So that means when the x value is positive, it's like an identity function. It will give whatever x is given as input. And when the x value is negative, it will output 0. And there is no saturation problem for large positive input. But then when the values are negative, it will become the neurons will not have any update. Now, in case of So to prevent this, you can initialize with some positive value. You can add some positive value to prevent this zero update issue. So a modification or a update to the ReLU is this leaky ReLU. It will prevent this zero update for the negative value by taking this alpha times x or 0.01 times x. So this 0.01, in case of a parametric value, you can treat it as a parameter during training and find the value of alpha that is good for your data set. So for this one, there are no problems near large positive or positive inputs, and empirically it determines the leakiness, and so you can make the alpha value a hyperparameter and then tune it for your data set. Then LU is a modification again. So for again, one issue is that the exponential function, it will saturate for large negative value. Otherwise, it retains all the other aspects of the ReLU function. So these are some of the most commonly used activation function in deep learning. Now coming to the learning rate delay. Now so even though sigmoid has many issues as mentioned in the lecture, we use sigmoid if we want the output to be a probability value, because it will give the output in the range of 0 to 1. Now coming to learning rate decay. So the learning rate is what is controlling the step size during the gradient descent. That is, we have W is equal to W minus alpha times whatever is the loss function, the gradient of that loss function with respect to the W. Now this learning rate is a critical factor in training the algorithm. The learning rate should not be too large, because if it is too large, it will result in a lot of oscillation and the network may diverge, it will not converge. But if it shouldn't be too low as well, then that will result in very slow update of weights. So it shouldn't be too large or it shouldn't be too low as well. Now in the last class, we discussed what is an epoch. Epoch is one complete pass through the entire data set. So there are different ways of selecting the learning rate. One way is to randomly start with some value and then gradually decrease the learning rate as the number of iterations increases. So you can also reduce the learning rate by a constant factor at every epoch, or every k epochs we can reduce the learning rate by a constant factor. Alternatively, we can also check after reducing the learning rate what is the validation error, and then based on whether the validation error is decreasing or not, based on that we can adjust the learning rate. Now one way to adjust the learning rate is given by this method. For a smooth decrease in learning rate over epochs, we can use this formula. So this is the initial learning rate alpha 0, and decay is some constant value that we can set, and epoch is how many ever epochs. So after every this number of k number of epochs, you update the learning rate. So that is what the epoch is for. So these are different ways of updating the learning rate decay. So here alpha 0 is the initial learning rate, and as the epoch value increases, the denominator will become large, and then gradually this learning rate will reduce, because the denominator, once epochs increases, the denominator will become large. So 1 by the denominator will become very small value, and that's how the learning rate reduces. So, learning rate itself could be a hyperparameter. We can also choose learning rate as a part of our grid search to find with what learning rate is good for our data set. Then coming to weight initialization. So there could be poor weight initialization. You can randomly select some weight. Uh, One issue with that is poor weight initialization can cause the training to fail entirely, even when we have a very good model and all the other parameters. Now, why weight initialization is an important factor is because there are large number of weights in the neural network, leading to a large search space for the minimum of the loss function. So we should not just randomly initialize, but it should be an efficient. There should be an efficient way of initialization of weights to converge to the proper minima value. So there are different ways of initializing the weight. A naive approach is to sample weights from yeah. So dk is any value. So dk could be a constant value, or it could be a parameter that you can set as a hyperparameter. It could be anything. It's not like there is a predefined value for dk. We don't know what decay is good for our data set. It varies with data set. And we also don't know what is the number of epochs that is good for our data set. So all these are factors that we don't know. So it's always like trial and error. You do this and then you find the specific decay value and epoch value. And then you apply this for the learning rate decay. So then, weight initializations, I was talking about naive approach. So in the naive approach, we select some sample weights from a standard Gaussian distribution, and this will have a mean 0 and variance 1. And we also need to normalize the inputs to have unit variance and single unit variance and zero mean. So then the issue is that yeah, so assume that the input x also has been appropriately normalized to zero mean and standard deviation. The issue is that the variance of the z will grow as the number of so suppose if I have the z, which is the activation, which is sum of wi xi. So I take weight from a Gaussian distribution, which is of zero mean and standard deviation 1. And I also normalized my input between 0 and 1. So this is normalized and this is normalized. So the variance in this one will be variance will be 1, and this one will be also 1. And then this is done over the full number of samples. So Z will be proportional to the number of samples. So that means uh, the variance of Z will grow with the number of inputs. That means when we have very large input, what happens is like this in the sigmoid. When we have a very large values, it kind of saturates, and then if saturation occurs, then the gradients will become 0 and the weights will not update anymore. So that is one issue with this naive initialization. And as mentioned in the lecture video, uh, the one way to prevent this is to use this number of, uh, you divide it by the number of inputs m, so that you get finally the variance as 1. So m into 1 by m. So you get a variance of 1, and then the Z value will not become, the output will not become a very large positive value, which will prevent the gradient update. Now, another way to initialize weight is failure initialization, and this is done by selecting the variance as 2 by the number of input plus the number of outputs. This is a standard method that kind of work with almost all the different kinds of problem. So this is the number of inputs and number of outputs from a specific layer. So that is how that is one way of initializing the weights. Then coming to data normalization. So before we give the data to the neural network, we need, so as we mentioned yesterday, it's good to visualize the data to see the features, and also how does the features vary. Some features might have very small value, some features might have very large value. So you can see the scales of different features. And if the scales of different features do not, I mean, if they are all not in the same scale, then it could be a problem. So one thing that we do is normalizing the data. So this is the so one of the way to do this is this z-score normalization. So what we do is, if there are n data points, there are n dimensions or features, we calculate the mean for each of the feature, and then we subtract from each of the feature value this mean. And then finally, we divide the mean by the variance of each feature. So I have, say, feature 1, feature 2, feature 3, etc. And each of this feature will have some value. So this is 10,000, this is 20,000, this is 30,000, etc. And then my feature 2 will have values 1, 2, 3, etc. Now I take the mean of this one. So I get some mean mu1, and mean of this one, I get some mean mu2. Then what we do is we take each of the value. This is x1, x2, etc. So then x1 minus this mu1 divide by, we also find what is the variance of this feature f1, that we divide. Similarly, for this one, we take the x1 feature, which is 1, minus whatever is the mean mu2, divide by whatever is the variance of f2. So this is how we do the z-score normalization. So after normalization, the values will have a mean of 0 and a standard deviation of 1 after doing this scaling. Now, there are other different ways of doing normalization as well, like principal component analysis. It's not really a normalization thing, but it uh, it's a way of scaling your data in a different way, so that portion sir has mentioned, he will be explaining it in the further lectures. So, yeah, like I told, it's good to normalize, because sometimes we might have data in the range of 1 to 1000 and another in the range of 10,000 to 10 raised to 6 value. So the scale varies a lot. So in those cases, we can do normalization so that all the features are in the same range. So one Yeah, so if x1 is ranging from 1 to 1000 and x2 is ranging from 10 raised to 3 to 10 raised to 6, then this w1 x1 plus w2 x2, this will be dominated by this x2, because the value of x2 is very large. So the optimization then should adjust w2 to be very small value and w1 to compensate. But this will be very hard, and it is very slow. So normalization can help in that scenario. And once we normalize, then the convergence in the gradient descent that will also become faster, and it will prevent the saturation that's caused by large Z values in the output, which will saturate this sigmoid tanh activations, etc. Now there are other another set of methods as well, like for example, min-max scaling, which will scale it to 0 to 1 or -1 to 1 range. Uh, Now another type of normalization is this patch normalization. So this is considered as a separate layer. We have the what we have the simple layer which does this sigma WI XI calculation. So just like that, this does a similar kind of layer operation, um, where you for a layer it will take the input X and then find the mean over those input. So it will take, so every layer will receive an input which is a mini batch B. It will take that input, find the mean, and then find the variance, and then subtract the mean and divide by the variance, and then uh, it will scale and shift. So it will find this, it will use this scaled value, and then multiply it by two parameters, multiply it by parameter gamma and add it by a parameter beta. So these two, gamma and beta, again are hyperparameters that we need to find from the data. They are not any fixed value. Uh, they also need to be found out from the value. Yeah, so we do this so it is again, so as I told, you do this Wi into xi in each layer. So just like that, this is also doing this gamma times the transformed value plus beta. So this is how the algorithm works. It's treated like a separate layer which does the same kind of transformation like Wx plus b, where X is your input. So it's like another layer. That's why it is doing this affine transformation on the mini batch, considered as another layer. So then, so this gamma and beta, they are trainable parameters, and we can find it through training. So batch norm is, it's not like we should always use batch norm. Depending on the data set, we may or may not use batch norm, whatever is working for your data set. So it helps. Again, batch norm has certain advantages and disadvantages. Advantages, as discussed in the video, it helps increase learning rate, it removes the dropout, and it improves the stability, it achieves higher accuracy. And it requires, because one extra layer is added, it requires extra computation. And it has been found that in small batch size, there were no effect on the on batch normalization. Okay. Then in the next set of videos, this recurrent neural networks are discussed. So when we consider sequential modeling, there could be one input and one output, which is one to one. One input and many output, which could be one to many. Again, many input and one output, many to one. And then many input and many output, many to many. And then many to many, many input, many output. So RNNs, they are they have a very simple. So this is taken from this source. You can check this. The notes there are really helpful. And also this CS231 notes, you can check for reading about this more. So they RNS, they accept an input vector and it will give, so they take an input vector X and it will give an output vector Y. But this Y is not just dependent on the X alone, but Y also depends on another factor, which is the entire history of inputs you have fed in the past. So for RNN, so this is the structure for vanilla RNN. It is called vanilla RNN, which is because it is the basic structure without adding any flavors. So you give the input xt and you get the output yt. But then this yt is a combination of both xt as well as ht minus 1, where ht minus 1 contains some information about the history of the inputs. So here the W is the weight matrix and U is the weight W is the weight matrix for the HT minus 1 and U is the weight matrix for XT and G is the activation function and mostly TANH is used. Then at the output we again have a weight matrix V and that is multiplied by this HT and that we have a optional activation function we can have. So so this is a simplified vanilla RNN. Now vanilla RNN, it has trouble with vanishing or exploding gradient. So in back propagation, it is difficult to calculate the gradient in the deeper layers. So exploding gradient is when the gradient becomes too large, then it will result in exploding gradient issue. And one way to solve this problem is to use gradient clipping, like you clip the gradient between certain range of value. Another one is this vanishing gradient, where your gradient becomes very small and there will not be any weight update. So for this, they have suggested two architectures. One is this LSTM and another is the gated recurrent unit, GRU. Now for a simplified GRU, as mentioned in the lecture, you have this X as the input and HT minus 1 is the past output. The state that contains the past history, the history. So we take the TANH of that and then we take a linear combination of this output and order computation. That is, we take one parameter 1 minus lambda times the vanilla output and lambda times whatever was the past HT value. Now, how do we find this lambda value? The lambda value is found in this way. So the lambda value is found by taking the sigmoid of WF HT minus 1 plus UF of XT. So this is the simplified gated recurrent unit and this F which is used here is lambda and that is the forget gate, that is called as the forget gate. It tells you how much you want to forget the past or how much you want to retain the past. So when lambda value is here, it shows when lambda value is 0, that means it will completely retain the vanilla output. If lambda value is 1, then it will only give the older output. That is why it is the forget gate. Now, this is a simplified version of the gated recurrent unit. In the actual gated recurrent unit, there is also a remember gate, which is again found by this taking the sigmoid of a specific, remember, weight matrix and UR of xt. Now, another variation is this long short-term memory. It again has somewhat similar structure, but then there is a memory cell, CT, and here again, these set of transformations are applied where you find the HT by taking the tanh of the CT with the output, and then HT. So then the CT is found by the forget gate times the cell state that is there before, plus the I is the input, and then the activation, which is the tanh of ZG. So yeah, so again, when we compared it to a vanilla RNN, which had only two weight matrices, here we have eight unknown weight matrices, and the number of weight matrices is greater in LSTM compared to GRU and vanilla RNN. So this takes more time for computation as well. I think it's good if you go through the video to understand this better, because has really explained it well. And now, why this LSTM and all work for um, this sequence to sequence classification is that it provides an alternate path for the gradients to flow. So one issue is this vanishing gradient, and by giving the past history and keeping the memory in the cell state, it's giving an alternative path for the gradients to flow. Now, there are variations of this RNN, which includes deep RNN and also bidirectional RNN. Deep RNN means instead of just one state that keeps the history, you can have multiple layers of like the units can be different units can be stacked to form a deep RNN. And then bidirectional RNN is where you, instead of just focusing on the past, you also focus on the future. So just like before, where we had W and HT minus 1 for the past, you will have W and HT plus 1 for the future. So as shown in the video where sir talks about this example, here we don't know whether like what letter this is, but once we know that this is P, we can know that this is a specific letter F. So then, for such kind of applications, it's useful to use bidirectional RNN. Okay. So now we will start discussing some of the previous year assignment questions and also some practice questions. So maybe I'll start with some of the initial part questions, and then yeah. So which of this is true with respect to activation function? ReLU is a linear activation function. tanh has a range of 0, 1. Activation functions enable neural network to learn nonlinear features and perform complex tasks. Sigmoid has a range of -1, 1. Yeah, so if we take the first one, ReLU is not a linear activation function. tanh has a range between -1 and 1. Sigmoid has a range between 0 and 1. So this is the correct answer. Activation function enable neural networks to learn nonlinear feature and perform classification. So the question is, a leaky ReLU neuron has alpha is equal to 0.05 and receives a pre-activation Z is equal to minus 10. What is the output? A is 0, B is minus 10, C is minus 0.5, D is zero point 0.5. So a nonlinear function is anything. So a linear means something that you can explain with the help of a line. Nonlinear would be anything that doesn't fit into that line. You need a curve to express it. So for example, sigmoid is a nonlinear function means it's not a line. Sigmoid doesn't, when you plot the function, you don't get a line. It's a nonlinear. It's a curved function. So that is mainly what we mean by nonlinear function. So for leaky ReLU, it is maximum of alpha times uh, x. Yeah, it is P ReLU because it is alpha. So when the value is negative, it will be alpha times whatever is the value. So here the value is z. So it will be alpha times z, which is 0.05 into minus 10, which is minus 0.5. So what is sigmoid of 0? Yeah, as we know from the curve itself, it is 0.5. What are the key differences between Savior initialization and naive initialization in the context of neural networks? Savior initialization maintains the variance across layers, while naive initialization sets the weight randomly. Savior initialization initializes weight based on the number of input and output, while naive uses a fixed standard deviation. Naive is suitable for deep neural network, whereas Savior can lead to vanishing or exploding gradients. Savior initialization samples weight from a Gaussian distribution, while naive initializes weight uniformly. Yeah, so it is Savior is based on the number of input and output, whereas the naive is based on a fixed standard deviation. So there's a layer. The layer has 200 input and 200 output. So what is the Saver initialization standard deviation? It's not the variance that is asked, the standard deviation. Yeah. So the variance will be 2 by the number of input plus the number of output, and it is 200 and 100. So it will be 2 divided by 300. And then for standard deviation, we have to take the square root of the variance. So whatever value we get from this one, take the square root, that will be the standard deviation. So the answer is 0.0816. So there is another type of initialization like Savior initialization. It is called as He initialization. So you can see this when you use PyTorch and all, you can see this He initialization. So they are all defined by default. So He initialization sets variance of the weight as 2 by number of input. Okay. So for a layer with number of input equal to 128, what is the standard deviation of weights? Zero point zero 0.0781, 0.1250, 0.0156, 0.0625. Yeah, so it is variance is 2 by number of input 128. So 1 by 1 by 64. Then standard deviation is square root of this 1 by 64. So it is 0.1250. Assume a smooth learning rate decay model given an initial learning rate 0.1 and a decay of 0.01. Find the new learning rate after 65 epochs. 0.08216, 0.07143, 0.09389, 0.0606. Uh, so it's for the weight initialization. Key initialization is a specific type of initialization, like Savior initialization. Now you can check it in so these are all defined by default in many of the deep learning library like PyTorch, TensorFlow and all. So when you use it, you can just specify the init as key, savior, etc. So then what it does is this transformation. So the initial learning rate is zero point 0.1, decay is 0.01. What is the new learning rate after 65 epochs? So we had that formula alpha 0 divided by 1 plus dk into epoch. Yeah, so this is 0.1 is the initial learning rate. The decay is given, it is 0.01. So 1 plus 0.01 into 65. 1 plus 165. 7.65. So is around 0.0606. So given an initial learning rate zero point 0.2 and decay is 0.02, what is the learning rate after 50 epochs? Yeah, so it is again direct application of the formula. It is 0.1006. So here, after training for 40 epochs using a smooth decay rate of 0.025, the learning rate is measured at 0.05. What was the initial learning rate? 0.05, 0.10, 0.20, 0.15. Yeah. So here instead of alpha, alpha 0 is asked. So alpha is given to be 0.05. So 0.05 is equal to alpha 0 divided by 1 plus 0.025 into number of epochs, which is 40. So when you calculate this, you get alpha 0 to be 0.10. So given an input feature set with data 10, 20, 30, 40, 50, what would be the output after performing Z-score normalization? And then there are 4 choices with 5 different values. So when we have Z-score normalization, we have to do x minus mu by sigma. And mu is the mean, and this is the standard deviation. Yes, so here the mean is given by 10 plus 20 plus 30 plus 40 plus 50 divided by 5, that is 30. And for finding the standard deviation, we take the square root of 10 minus 30, the whole square, plus 20 minus 30, the whole square, plus 30 minus 30, the whole square, plus 40 minus 30, the whole square, plus 50 minus 30, the whole square, divided by n, which is 5. And then this will be 400 plus 100 plus 0 plus 100 plus 400 divided by 5. So this is approximately 14.14. Then for each value in the input, we subtract the mean and divide by the standard deviation. So I'll do it for one value. So the Z-score value for 10 will be 10 minus 30, the mu value, divided by the standard deviation 14.14. So it will be approximately equal to minus 1.4142. So the correct option is D. So after applying a Z-score normalization to any data set, what is the mean and standard deviation of the resulting normalized values? Mean is 1, standard deviation is 0. Mean is 0, standard deviation is 1. Mean is 0.5, standard deviation is 0.5. Mean varies, standard deviation is 1. Yeah, so independent of the original data value, the Z-score normalization always produce a data set that has a mean of 0 and standard deviation of 1. The resulting normalized values will have a mean 0 and standard deviation 1. If you have doubt, you can take these transformed values and see what is the mean and standard deviation of these 5 values. Then you will see that the mean is 0 and the standard deviation is 1. A feature has a training set mean is equal to 20 and standard deviation 4. What is the Z score for X is equal to 28? Yeah, so it is 2. 28 minus 20 divided by 4, which is 8 by 4, 2. So why must the mean and standard deviation for normalization be computed exclusively from the training set? And then you have to apply that to the test or validation set. Uh, yeah, so the answer is C. It is to prevent data leakage because uh, so we usually split the data into training, test, and validation set. And usually we may unknowingly apply normalization before the splitting process. Then, if we do that, it will result in data leakage. So, always we should split the data into training, testing, and validation. And then we should apply normalization exclusively on the training set only. And then you should only use the transformation on the test validation. So if any one of you have used the scikit-learn, is uh, any one of you have used scikit-learn for any machine learning classification? Um, have you used this in Python? Okay, I think only one person has used. Okay. Yeah, so if you have checked the function for normalization in scikit-learn, you will see that some normalization dot fetch and then some normalization dot transform. So this is what this question is about. So the fitting is where you should apply the training data. That is, you should apply the normalization on the training data. And then by this fitting process, we find from the training data what is the mean and the standard deviation. Then you apply the uh, transformation, the normalization using this mean and standard deviation we found from the training samples to the test or validation data so that the mean and the sigma, the standard deviation are found only using the samples from the training data. It will not contain any sample from the testing data. So that is how we prevent data leakage. So if it includes the testing data also, then the mean and the standard deviation will change and the model will get some information about how the test data will look like, which will result in poor generalization. So this is one important practical aspect when we do normalization. Which of the following statements accurately describes a benefit of batch normalization in deep learning? Batch normalization helps speed up the convergence of neural networks during training. Batch normalization reduces the complexity of the network architecture by eliminating the need for activation function. Batch normalization improves model generalization by reducing overfitting. Batch normalization is primarily useful for pre-processing raw data before feeding them into new. neural network. Data leakage is so you have the so you split the data into training set, testing set, validation set. So you don't mix up the training set and the testing set, right? Because you make the model, you give the model the training set so that the model learns what the pattern look like. But then the model should see some pattern that are outside of what it has learned from. That is the test set. So if you give some parts of test set to the training set, then that is what is called as a data leakage. So the model will already have some information about what the test set will look like. So it will kind of see, okay, the test set is looking like this. So then it knows already the pattern of the test set, and then it will give a good performance. But that actually does not give you the right performance because there is already some leakage of data. So batch normalization helps in uh, better training and leads to faster convergence. So the answer is batch normalization helps speed up the convergence of neural network during the training. So in batch normalization, which two parameters are learned? So batch normalization I have explained before. So it is mainly used. So you have your activations from the previous layer. It might have the activation might have very large value, and it would be good to make it into a certain range, that is to normalize it so that your gradient updates will become faster and it will help in convergence of the weights. So it is treated as a separate layer where you have two factors just like the weights and the bias in a neural network layer. So here we are asking what are those two parameters that are learned during the training through backpropagation in batch normalization. So those two parameters are scale and shift, which are gamma and beta. So this is one question that sir asked in the video. So if you have watched the video, you might be able to answer this. So where is batch normalization typically inserted in a standard neural network? Yeah, so it is kept in between the linear transformation and activation function. So after the linear transformation, if there are very large value, then when it goes to activation functions like sigmoid, if it is a very large value, where will it land? It will land in this saturation region, right? So to prevent that, we use a batch norm in between so that the values are scaled between a specific range. And when we apply the nonlinear activation function, it will not go to this saturation region, but it will be somewhere over here so that the gradients will be properly updated. Yeah. So then, one more question. That's So, a researcher trains a model using a mini batch size of 2 with batch normalization. What problem is most likely to happen? The model will immediately overfit the training data. Batch statistic will be too noisy to be meaningful, making the batch normalization ineffective. Model will train much faster. The gamma and beta parameters will diverge to infinity. Yeah, so in batch normalization, so in that algorithm, we are seeing that it computes the mean and variance over a mini batch. And here we have only two samples. So then the statistics will be very noisy and they may not determine the actual or they may not represent the actual data distribution. So the batch normalization will become inconsistent across batches and it will uh, in fact might destabilize the training. So the answer is it will be batch statistics will be too noisy to be meaningful, making the batch normalization ineffective. So it is recommended to use batch normalization when there is a batch size of 16. Minimum batch size should be 16 to 32. Then, in the previous year assignment question, there is a diagram given where there are inputs like this x1, x2, x3, etc. over time. And they have given the values of first three inputs x1, x2, x3, and their corresponding y1, y2, y3 is also given. And then the matrices, the input is multiplied by the U matrix and the H value, the hidden state values are multiplied by W and the resulting calculation is multiplied by V. So those matrices are also given here. And they have also mentioned that the activation function is tanh. And activation for the output is a linear function. So no special activation. So this is the question. So x is zero point 0.1, zero point 2, zero point 3. Y is 0 0.5, 1, 1.5. The first question is, what is the value of hidden state at time step t is equal to 1? So what is h of 1 or h1? So we have to assume that the initial h value is 0. The initial h0 is 0. So then what is the ht value is the question. This will be 0 because we have for h0, 0, 0, 0. So we don't have this factor. Only we have this. So u is given by 0 0.1, 0 0.2, 0 0.3 and x is we know 0 0.1, 0 0.2, 0 0.3. So u into xt we have to do. So then we get 0.1 into 0.1 plus 0.2 into 0.2 plus 0.3 into 0.3. So we get tan h of 0.01, 0.04, 0.09. So that is tan h of 0.01, tan h of 0.04, tan h of 0.09. So now you can check what is the tan h of 0.01 using the formula for tan h. So the answer will be 0.0099, 0.0199, 0.0299. So now the next question is, what is the total loss for this sequence? So in the sequence, we have x1, x2, x3. So y1, y2, y3. So we should compute the loss for each of them. The loss for y1, the loss for y2, the loss for y3. So then we can start with x1. So we can take the activation for x1 as u times x1. That is given by u is zero point 0.1, 0.2, 0.3 times x1 is 0.1. So you get activation as 0.01, 0.02, 0.03. Similarly, uh, for the other one, A2, it is u times x2. That will be 0.02, 0.04, 0.06. Similarly, for A3, it will be u times x3, 0.03, 0.06, 0.09. Okay. Now, we have to take the tan h of this A1, and that is the hidden state H1, because the initial hidden state is 0, 0, 0. So that this portion will get 0. The only portion that remains is this. So we take the tan h. So H1 is tan h of A1. So you have to calculate tan h of this. And then H2 is tan h of this. And H3 is tan h of this. So once we have the tan h, we got this part, right? We have this H1. Now, to get the output, we have to multiply the H1 by V. So, O1 is V times H1, O2 is V times H2, O3 is V times H3. So, V is given to be 0.7, 0.8, 0.9. So 0.7 into this H1 that we got, zero point 0.8 into the H2 that we got, 0.9 into the H3 that we got. Now, the output Y hat is, so there is no, there is no activation function after this O. So it is just linear activation. So whatever is there in the O1, it will be the same as Y hat. So this is approximately, when we do this calculation, you should get approximately 0.04976. When you do this, you should get 0.223. When we do this, we should get approximately 0.6769. So this is the prediction for y1, y2 and y3. And the actual y is 0.5, 1.5. So actual y is 0.5, 1, 1.5. Then we find the mean squared error between these two. So y minus y hat the whole square 1 by 2 sigma times y minus y hat, where I from 1 to 3. So you substitute 0.04976 by, sorry, minus, so this will be the mean square error, and this will be approximately around 0.74. So it is the same as the, so you just have to calculate the, substitute in the equation for RNN, the LSTM, and then we'll find this. It's a very straightforward calculation, especially for the first few sequences. Okay. Then next question is, what is the value of dou L3 by dou V? So dou L3 is here. The loss is calculated here uh, for the third input. So that divided by V. So dou L3 by dou V is equal to dou L3 by dou O3 into dou O3 divided by dou V. Now dou O3 we know it is just H into H3 into V, right? So when you take the derivative of this with respect to V, we get only H3. Now this is the 1 by 2 y minus y hat the whole square. So that 2 and 2 will get cancelled and you get y3 minus O3 into H3. So then we already have what is uh, y3 and O3 from these calculation. So H3 also we can substitute it here, and then can you tell what value you get? So you should get minus 0.1403, 0.2268, minus 0.3083. Mhm. There was one more assignment question. In the context of deep neural network, how do LSTM and RNN differ in terms of handling gradient flow? Yeah, so LSTM mitigates the vanishing and the gradient problem better than RNN due to its gating mechanisms. That is the correct answer. So there was one question that we left in the beginning. What is the key advantage of using bidirectional recurrent layers in an RNN? Improved memory efficiency, faster convergence during training, reduced computational cost, access to information from both past and future. So bidirectional recurrent neural network, what is the advantage? No, so bidirectional recurrent layers are used to access information from both past and future time step. It is bidirectional. That means both past and future. So what is the technique that is used to address the exploding gradient problem in RNNs? Dropout regularization, Savior initialization, gradient clipping, patch normalization. Yeah, so gradient clipping is used. That is done by checking what is the value of gradient. So if the value of the gradient is greater than certain set gradient maximum value, then we clip the gradient to a certain range, minimum and a maximum. Uh, so in GRU, the equation is given by 1 minus f into g plus f into ht minus 1. So when the forget gate is close to 1, what is the effect of the output? Like what will happen to the output? That is the question. So when the forget gate is close to 1, what happens? So the equation is given by ht is 1 minus f into g plus f into ht minus 1. So this is the forget gate. Yeah. So when f is close to 1, this term will become very small and it will be mostly the previous state value with very little new information incorporated. So this is like question number 7. So you have u and x1. What is the hidden state? H1. Assume that h0 is 0. So what you have to find is h1, which is tan h of u times x plus w times h0. This is 0. So you have only this part. So h1 is tan h of ux and x1 is given to be zero point 0.1. So you have to tell what is h1. Okay, so when we do this calculation, these values, if you have seen, it is very small, 0.02, 0.03, 0.04. So this is approximately equal to 0.02, 0.03, 0.04. So the answer is 0.02, 0.03, 0.04. So, so no, we don't always need to use TANH, but TANH is one of the most commonly used activation function for the H calculation. Uh, yeah, it may depend on again the application, but TANH is the one that is most commonly used. Mhm. So thank you all for attending. We'll do the next session on Tuesday, 7 p.m. to 9 p.m. Thanks.